都改了对吧？
已经有这个可以直接就是说你自己给它一个新的一个 CI 的发力，包括实际上现在我们在做那个。
Sorry?
一个叫做上一
No, it's a presentation. So 3%, 1, 2, and 3.
去直接去把这个
Oh, so using the handheld mic so we can just pass around?
想那种 CI 的其实把它最大的这个对比。然后其实这个 CI 这个东西呢，就是给大家很多的这个自由度。然后如果你不去追求保证这个Kata 和 RunC 用同一个网络同一个 CI 的网络控制的网络走的话，那其实有很多灵活性东西可以走。原来我们自己也是把它就直接去插到自己的那个 OBN 的网络。
就这样的
对 CI 对，它是遵循 CI 的。
我咨询这个它一个网络问题啊，就是它现在目前能支持，比如说像OpenStack 服务类的项目。换句话说，如果涉及到这种 overlay 的网络，它是不是相当于在 Kata 里面
是这样的，它不需要 curl， 就是 curl 是这样的 ，curl 它是一个，就是它是想办法是把那个 user 的网络去透到网那个虚基里面，再给那个容器。就是说，实际上因为它可以做到和那个，它是可以和那个 Nova 的虚基搁到同一个 level， 所以在这样的情况下，它实际上就可以直接去建设这个网络。
但是如果它是一个 overlay 网络的话，是不是相当于它有2层 overlay
就是
嵌套？
它可以多层的 overlay 大家都行。
因为数主机有个 overlay， 然后我那个 Kata 所在的容器所在的那个虚拟机，所以也需要一个。
就是你可以把所有虚拟办它可以跑到虚拟办，因为它这样它可以直接接到。
介绍。没想讲我这个4点。
不会存在 overlay 嵌套。
可以想线，可以想线，就是你不想线可以不线。
肯定可以想线。
我介绍也行，隆重介绍一下。
我现在的移动元件知道吗？
可以买。
我11年的移动元件知道。
说中文。这么说像腾讯那个议题，
我们这里审阅还行。没事，我上来就说两句。说点。上来就说。起码介绍之前我跟你说。
岳哥听课，我讲课。对啊，您现在是？我在念课，我在课，我在这个。那我直接报。那我也是。哎，我可以，我给他知道。期刊员，这是第二代，是都不，刘兆德，我还在那上班，我现在苏博士，原来咱经常哦，苏博是吧？他给我打电话，太少了，是他们在讲4点多上火车，我先补上。来这边继续写电子，只收600多。你是哪个？
Hello, everyone. Good afternoon. First, forgive us to prepare this PowerPoint in Chinese because we thought there may be some simultaneous translation thing. So, but unfortunately, so let us to give this presentation both in Chinese and English. First, we give 200 node large scale OpenStack test results in Denver. And in the past half years, we continue to scale out our cluster to 500 nodes, and we continue to optimize the private cloud architecture in the big data workload. So today our topic is about improve private cloud performance for big data workload. First, let me introduce ourselves. We are glad to continue to collaborate with the Intel team so we can make the full stack optimization from hardware to software. We are honored to invite Dr. Liu to come to Shanghai to join us to give this presentation. And my colleague Dr. Su and me are both from INSPIR CDC Group. 我们非常荣幸的邀请到了这个宋义良博士，也是英特尔这个数据中心事业部的首席架构师，来和我们一起来给这个演讲。然后我和苏志远博士都是来自这个浪潮的数据中心集团。那么浪潮的面向这个政务、通信和金融的这个云的这种技术和产品支持，都是由我们这个团队来支持的。 Okay. First, the large scale cloud have become more and more important for the digital transformation of industry. 就是大规模的航云建设已经成为这种大企业或者是行业信息化转型的这个关键。这一方面呢，是对于一些大企业来说，可能由于这种降本增效的这种要求，它会越来越多的整合这种内部的IT 资源。那么它的信息化部门呢，也逐步由这种成本中心转变为这种服务中心，或是这种甚至是这种盈利中心。而把这种IT 资源通过这种供给的方式来提供给他下属的这种2级的公司或部门。还有另外一种场景呢，就是对于大的行业来说，它的这种头部公司，也希望能够整合行业内部的资源，那么希望能把这种通过这种云的方式，能够来提供这种共性的这种应用和数据的服务。这一页说的是就是就是云计算，其实它的本质是呈现出这种规模效应，就是说 the most important value of cloud is scale effect， 就是这个意思。就是云我们知道云计算已经发展了这么多年了，10几年的时间，那么云计算的技术也越来越成熟，那么它已经可以说走出这种幻灭期，是吧？进入这个稳定的成熟区，特别是对于私有云来说，现在已经进入这种落地的案例也越来越多。那么云计算本质上还是说，通过能够把大规模的这种资源统一的管理和调度起来，来提高这种运维的效率和这种资源的利用率。并且当前现在这个应用的这种融合创新和这种动态扩展的速度也越来越快，那么就要求这个云的对这种存储和计算能力的要求也就越来越高。那么就要求它也反过来会推动这个云的规模也会越来越大，从而使得这种云的边际效益会更加的明显。我们这个可能在原先在公有云下是比较突出的哈，现在其实在私有云的场景下，我们也做过一些统计哈，比如我们有一个case， 就是说在一个500节点的这个规模下，它的这个资源比较关键的资源critical resource such as memory， 它是70%的这个利用率。那么它的这个平均利用率是70%，那么它的这个超配比可以配到这个1.3到1.4，这样的话实际上它就能够节省大概这个30%到40%的资源，也就相当于能够节省这个100多台服务器的这个成本开销。那么对于大数据来说 ，for big data is such a kind of dynamic and large-scale workload for which is very which can be support a very 这个来回转换好难哈，就是可以为这个可以通过云为大数据提供这种天然的这种支撑环境。那么我们主要是说，我们通过这种云数结合，可以为这个云计算可以为大数据提供这种根据业务场景来实现这种组件的灵活组合，并且呢能够实现这种资源的动态伸缩，并且还可以通过这种负载的这种混合部署来实现这种就是白天和晚上这种实时计算或者批量计算这种灵活的转换。也就是说，这个大数据云计算为大数据提供了这种非常好的这种天然的这种支撑环境。但是呢，大数据上云其实还面临一个关键的挑战是什么呢？就是性能问题。也就是说，比如说这里最关键的其实就是这个磁盘的读写性能问题。我们做的统计就是在由于这个虚拟化的这种软件虚拟化的层次和这个现在这种OpenStack这种存储分离的架构，存储计算分离的架构，那么在虚拟机上这个跑大数据，比在这个物理机上跑大数据大概的性能会低30%左右。那么我们是如何进行这种优化的呢？下面请这个Leo和苏博士来继续进行分享，谢谢。
Sorry, first of all, apologize if you can't read Chinese, but the next few slides is in English. I'm going to talk in English as well. But just now, what Dr. Qi has explained is about the combination, the convergence of big data and large-scale infrastructure. So what we're trying to do is we first try to understand what is the gap, what is the performance opportunity that we can improve. We try to look at from big data, if you want to move big data workload into cloud, what are the challenges that we are facing? One of the things that from Inspur, when we're working with Inspur, we realized the storage is one of the bottleneck, right? 存储是一个问题. So storage is one of the bottleneck. There are other components as well. So what we're trying to do here today is to look at how can we how can we create a software-defined infrastructure. I don't need to explain the whole architecture. I believe most of us have seen this architecture many times. But what you're trying to do here is looking at my left-hand side or towards the left-hand side. We look at the platform features on the hardware. How can we expose those hardware features all the way up into the upper layers through the compute storage network layer into the software-defined infrastructures that can provision VM or bare metal, and including your block object file or even the SDN function that can take advantage of the underlying hardware features that can help you to boost the performance for the above big data workload. And in today's presentation, we are showing Spark as one of the examples. I think Dr. Su also will explain some Hadoop stuff later. But I will show you some of the results that we have tested on using Spark. So before moving that, trying to introduce the new technologies from Intel. This is what we call Intel persistent memory. So in Intel persistent memory, if you look at this triangle hierarchy, if you look at hard drive, it's milliseconds of latencies. SSD, microseconds latencies. But if you look at DRAM, it's about nanoseconds latencies. But Intel persistent memory is somewhere in between that DRAM and SSD. So what this technology is trying to solve the gap, as you see on the diagram here, is try to solve the gap between the DRAM and the Optane SSD. Because in traditional models, right, DRAM is volatile, right? If you reboot the system, you lost everything. But SSD, you can persist the data, but it's much slower than DRAM. So what Intel DC persistent memory can bring you the advantage is you can get a new memory speed, but you can still persist the data. That's a very quick summary. In DC persistent in the persistent memory, we have two operation mode. One is memory mode. The other one is app direct mode. The memory mode basically do not require any software changes. The memory basically the operating system basically just look at that as a system memory. Okay, it's just a memory. It's a very, very large memory. And in Intel, depending on the CPU model, you can support up to 3 terabyte of memory per CPU. So in one system, potentially can reach 6 terabyte of memory. The other one is what we talk about, the app direct mode. Basically, you expose the device to the software layers and the software stack, like for example, Spark or Hadoop, they will make changes. They will write the data directly into that payment devices, and that data will persist. So that's a quick summary of this technology. If you want to find out more information of this persistent memory, please drop by the Intel booth. We have some of our staff over there that can explain more details to you. So why I'm talking about this persistent memory? Because of PMAN, because of vPMAN support in Nova. So in train release, we work together with community partners like Inspur and other company that we upstream these particular features in the train releases. They're able to support using Nova to support the management or the allocations of persistent memory into the VM devices. So what we did here is basically you have a large persistent memory region that we slice them into different namespaces, okay? And every namespace is being managed by the Nova, and then this can be managed, exposed to the VM, individual VM. So as you see from the diagram, you can actually pre-create the namespace at a predetermined size, for example, 128 GB or 256 GB. So that's up to the operator to define that size. And with that size, then you can expose that devices to the persistent memory, to the VM. So VM, inside the VM, you run the application. So that VM can see that devices. They can take the best advantage of the performance that you can get from the persistent memory. So we did some experiment. So we test that scenario. If you see from the top, the most left-hand side, that's the VM with the VPMEM devices with 256 GB, and the one on the other side, the VM that is without the persistent memory. So what we done here is actually created a VM in two scenarios. One is with VPMEM, and then we run the Spark OEP software, and the Spark OEP can utilize the DRAM or the DCPMM as a cache memory to accelerate the SQL queries as part of a decision support system. So this is the experimental result, right? It's not optimized for anything, right? So but based on what we had used for our system before, you can see the performance that can help to improve the SQL, the Spark SQL queries in the decision support system. So basically, you can see two labels here. One is with VM without persistent memory. The other one is with the persistent memory. And in this scenario, we loaded about 640 GB of data size as a database size. And then we tested on VM with 1 to 8 GB of memory, and another VM with 1 to 8 GB memory plus 256 GB of persistent memory. And that's the performance you can see on the screen. So basically, in general, it can help to improve the Spark SQL in a decision support system. We tested with a decision support system with different kind of IO intensive queries. Generally, you can achieve about 30% to 50% of improvement in terms of query time. So that's what we have seen in the experimental result. So if you want to find out more, or if you want to see a demo, you can go to the Intel booth again. So they have a demo about this technology. And next, I'll pass to Dr. Su to talk about the general integration from the software and optimization from a software perspective. The one I've talked here is more on from optimized, then we have to integrate that into the software. So Dr. Su will talk about the software side.
Okay, thank you. So here it comes to the hardest part for the Chinese, and I try to explain my key points for each slide in English, and for the most detail, I will use Chinese to specify. So since we talk about the cloud and the big data, so we need to have a cloud and we need to have a big data platform. So for this slides, this our cloud platform is in called OpenStack, and also here's the architecture picture of our product, and here is some features of product. It's in called OpenStack, and we have new modulars and new programs for the OpenStack, which we try to contribute to the upstream community, and also we keep on focusing on the enhancing for the virtualization layer for the functionality and his performance in the KVM. And so also we have always tried because you needed to make the big data the data safe. So we also we also have some the high availability features in our product, and also the safe, and also the AI ops. Also this is for all the cloud thing. And for the next page is for our in-cloud insight, which is our big data platform. It's based on Hadoop and Spark. All these components you can see, and I do think that you can understand all the keywords in this program. Also, the key features for in-cloud insight includes the full scenario, can cover all the scenarios for vertical industry, and also we have the SQL optimization, and you can the data data warehouse for 1 TB. 1 TB, that's the 42% performance improvement in the performance, and also we have solid. Also we have multi-tenancy. This is based on our sales products, the multi-tenancy for big data, and also we have a unified user certification and assessment and management system. So this is big data. Just make it quickly. And the next is how we combine cloud and the big data together. So here, people here, I see you all know the Sahara. That's the program there. The Sahara can provide can provide big data services from OpenStack and on OpenStack, and now and also Sahara can do some scheduler, job scheduler. But in our case, I will think that the big data platform also can. Okay, so let me try to use this in Chinese first. Okay, it's hard to use it in English. So 就是我们认为在那个撒哈拉，其实它是有这个集成的框架，就是它可以提供大数据的服务，也可以做这种作业调度。但是呢，撒哈拉整体来说，它还是相对于说比较重量级的。对于这个服务来讲，它其实你如果说用撒哈拉的话，你会丢失一些这种我们在大数据平台上开发的一些这种大数据自身的一些调度属性。所以有时候你不得不撒哈拉它做的事情可能还不够，你还得切到这个大数据的那个平面上去做一些事情。那这样的话，我们索性不如说我们要轻量级，我们简化这个大数据的这个撒哈拉这个组件，对吧？我们借鉴了它的内容，我们只是用撒哈拉里边这种对外提供这种大数据集群的这个部分，然后呢，我们把集群管好。那至于作业的事，我们交给专业的去做，交给大数据去做。这是我们当时去做这个proxy 嘛，就我们引入了一个新的项目来做这件事情。就是我们觉得就是说，作为语音来讲，它关键是我把这个开放的基础设施提供好，对吧？我把这个基础设施提供出去就好了。就至于基础设施怎么用，那我们交给专业的人去，专业的东西去做专业的事情。So，这就是我们所以说我们在引入这个 proxy 嘛，这个组件的时候所考虑的。所以说它是相对来说它比撒哈拉更轻量级、更快速一些去做一些事情。So the key point for this slide is we think Sahara is too heavy, and we use a light program we named is Proxima, also to provide the management the big data clusters and for all the job scheduler thing, or for all the job submit or the job things, we just give back to the big data itself to do that. So that's our architecture here. And the next part is for how we optimize under the cloud scenario for big data. So just like Dr. Chi said, that the bottleneck for big data is about the storage I/O. The storage I/O thing. So we use you can see the bare disk directly. We just use bare disk directly in the virtual machine, and so you can see that there's less layers, and you do not need to go through the network for all the I/O in the cloud on the VM machine, and also we compared the bare disk mode vs the LVM mode. So you can see the LVM mode, you need to go to the LAN, you need to with the iSCSI. So there do will comes to with some what say so its performance is very less than the bare disk thing. For the bare disk to the VM machine, that's the performance is nearly to the hard disk. You just use directly without a cloud. And for LVM, you can see the bare disk mode. It's about 30% better than LVM. So I will use Chinese again. And 就是我们说这种我们就实践了2种模式嘛，一种是裸磁盘这种直通，一种是这种 ASCII 的这种 LVM 模式。裸磁盘直通给虚拟机用的话呢，它的性能其实比 LVM 会，我们经过实测呢是高30%左右。那因为这种 ASCII 它可以去优化这个 bare disk 模式嘛，它就是会裸磁盘直通模式会比那个LVM 模式会少了这种网络层的这个走网络，少了走协议层转换这个阶段。同时呢，也可以看到，如果说你用 Ceph 的话 ，Ceph 其实比 LVM 的那个协议站还深。你还会做到网络到分布式存储上，所以说那个性能更差。我们青岛就没有比。我们这块重点提升的是，我们在裸磁盘这种模式下，其实是能够达到接近于物理磁盘的性能，能够在云上去我们用虚拟机来实现这种灵活的扩展性，或者说大规模这种事情。然后同时呢，我们用物理磁盘的直通方式来满足它的这个性能要求，这是我们做的第一个优化。So the second one is about different cache mode for performance, the confluence on the performance. So as we know, that is about the 3 cache mode. That's about the now and write back and write through. Here is the architecture for different cache node. So for the now node here, you can see when you first we come to the write for the maybe this 4K write here, and you can see for the write back, they will write to the host OS page cache, and they then will come back to the application. So clearly that's the fastest way to do the for the write in this scenario. And now is kind of low because she needed to do the she do not need to the now can. Okay, I'll try to use Chinese here. 这个 now 模式呢，它是直接就是到那个物理盘的那个缓存嘛，就是我们有这个缓存，一个是 host OS 缓存，一个物理盘缓存，一个物理盘。now 的话呢，它是到那个物理盘缓存，然后呢再到物理盘，然后呢它再去返回，这样的话它的性能相对来说，它因为它要落盘嘛，它的性能会比 write back 会差一些。write back 它是直接到缓存就返回了，那个 write through 呢是直接到盘也没有缓存，那这样的话它的性能是最差的。那这是我们的结果，第一个结果就 write back 的性能最好。那第二个呢，就是说我们在看这个读的时候，读的话 now 模式的读呢，它是要直接是从那个物理磁盘的缓存去读，然后呢 write through 和 write back 的读呢是要先去，也是要走到的这个 host page cache 这一层去往上读。那这样的话呢，它读的时候理论上有缓存的性能是最好的。但是我们在实际测试结果发现，就是说这 now 模式的这个读取效率，在顺序读的情况下，比 write back 和 write through 都要高出2倍，它的性能是2倍。那这种情况，其实我们经过分析之后，觉得就是它这是由于缓存命中的影响，它要先读缓存，但是呢缓存里面没有这个说继续往下找，所以说一直到磁盘上找，它会性能会差一些，这是我们实测的。那这样的话，就是说在 now 模式下，它的读的效率是最高的。So for the read, so the now cache mode is better than the write back and write through. 我们在这种云的这个场景下，云数场景下结合分析呢，就是说我们发现这种顺序读的这个操作场景，顺序读写的这个场景比例比较大一些，所以说呢，我们就是说顺序读的相对来说更多，写的相对更少，因为我是从这个云上把数读出来到我的这个大数据平台上去分析嘛，相当于，所以说呢，我们就是说综合来推荐的话，如果说在云上的这个数据性能，如果说是那个对要求比较高的话，我们推荐这种裸磁盘和这种 now 的模式。同时呢，在这种情况下，我们知道裸磁盘直通的话，虚拟机可能是不能迁移的。那这种事情，这种其实迁移最重要的目的是为了这种资源的这种平衡和调度嘛。那其实我们觉得，就是说大数据它自身其实也有一些调度的机制和一些load 一些 load balance 的算法，可以满足这个虚拟机不能迁移的要求。So the third key point here is in the big data scenario on cloud. So the sequence read is take the most percentage. So we recommend the non-cache mode bare metal disk, bare disk directly to the VM to meet the requirements for the high read and write I/O here. Since we talk about the software for VM optimization, and also big data is quite is a typical large scale scenario for the cloud. So we have 500 nodes, like Dr. Chi said, we have 500 nodes practice on OpenStack here, and we do have some test cases like here. I will translate it by one. So the first one we have the deployment efficiency and test, and it's about for how long time we deploy 500 nodes, and the second one we have the large concurrency test, like we have 2,000 VM creation concurrency for 500 nodes to check the replicate the database nodes can handle that kind of expression, and also can have some concurrency to create volume concurrency or create a network, and in that kind of situation is our monitoring system can bear that kind of request. And also we have the high density test, and we have some performance test, including storage I/O test, network I/O test, and the network latency test. And also we have the stable test for control panel and data panel, and also for our data for the high performance, the performance of our high availability. So I just show some test results here. If you want to know more detail about our 500 nodes test practice, you can visit our booth, and also you can visit here. We have a special topic about our 500 nodes test here. I will show this slides later. And here we show some results. The first one is about the high efficiency deployment. Actually, you can see for the 500 nodes we just use 5 hours to install the OpenStack, because we actually here we use colon symbol to do that things, and also for the for the distributed storage we use 3 hours. That's about 77 nodes about Ceph, and about and for all the next is OpenStack nodes. And also we if the reconfiguration for 500 nodes we only need to 40 minutes, and also we for the scale, we first we deploy 300 nodes, and we scale another 100 to in 1 hours. We scale in 1 hours, and also we try to update the version for this in this scenario. That's 3 hours. And the next is the result of high performance control panel for I just show two results here. This is a 3000 VM concurrency current. You can see all this is 100% success. And also we have another test is about when there is already 20,000 virtual machines existed in the 500 nodes in the OpenStack Cloud, and then we try to 1,000 concurrency of creation for VMs, and also it's quickly, and it's with 100% success. And the next is about our high availability of services here. In this one, I think so, the high availability is a kind of old story for OpenStack now. And in this, in our test scenario, we try to rack scale. I mean, you mean the rack scale power off. I think. Yeah. So a level about 10 computer nodes in one rack, and there are totally 180 VMs. And when we power off the whole rack, and the other VMs are evacuated in 5 minutes. And also we use we scale the scale of the high availability clusters after the optimization. We make it from the 16 to 256. so 这个就是我们说整机柜断电的这个，我们在就是说把它那个时间调到降低到5分钟，这个是很快的一个速度了，180台虚拟机5分钟之内完成。然后呢，我们再引入这个pacemaker 做 pacemaker remote 之后呢，这整一个的这个高可用集群的规模是到了256个节点，是一个集群，这是一个简单的结果。另外一个 the other one is about the high performance of network here. So this is a lot of words on this graph, and basically if you want to very low latency and very low就是let me see 的丢包率这个事情 ，you need to optimization from hardware to the hypervisor and to the guest OS. So mostly for the core, for the cache, so many parameters to tune to achieve this kind of result. So this is the high performance network here, and then I will try to introduce all these works are based on our cooperation between INSERP and Intel. So for the next we will focus on the cloud computing, big data, and deep learning. For this, we call this like a smart computing of INSPER. So we will focus on that, and we try to provide more services and more optimization for cloud, big data, and deep learning here. And that's our next cooperation for the future here. So here you can find more details of what we talk about here, 500 nodes, and more detail about hardware optimization, software optimization. Please visit our booth, and you will get more. Okay, thank you. So do you have any questions for any of us? Okay.
那个裸磁盘是这样，我们就相当于是OpenStack 只支持 LVM 嘛，是吧 ？LVM 他们是通过这个要起一个 ASCII 的这个服务，对，这样相当于还是要过一层这个网络。我们其实开始测了，就是说不通过网络，只从本地来实现，就通过这个调度到本地来实现，但是性能还是因为还是要有经过网络站，并且还要经过 LVM 那一层的管理，还是有损失，所以我们直接就是通过这个从 QML 里边直接挂它的这个磁盘文件的方式来实现。这个实际上和挂那个裸磁盘是类似的这个效果。这个我们当然要改这个 Nova 的代码。刚才那个刀叔介绍就是，如果是在这种场景下，它需要是依靠大数据本身的，就像 Hadoop 它本身是有这种 checkpoint 机制，或者它数据层面是有这种多副本机制来实现数据和它的这个应用的这种高可用，就不再需要通过虚拟机的这种迁移的方式，因为你即便迁移，我们测过，你即便迁移过去，它能把原来的业务恢复，其实也是一件很复杂的事儿，这个可以通过它的这个本身的 checkpoint 机制来实现。这个相当于你得把大数据布在裸机上，是吧？布在裸机上，你如果一个物理级挂掉，那其实它是有这种 checkpoint 机制的，有这种故障恢复的机制的，也不需要你的裸机层面去做什么事情。 不，大数据本身是有这种容灾机制，这哈杜夫这一套框架是有本身的容灾机制，故障恢复机制，对。对。你好。对，刚才其实有一点可能没解释清楚，就是说我们前2页是在导这个，是在说这个大数据其实是上云其实是一个大数据的一个算是强需求吧，因为它能提供这种什么呢？能提供这种多租户机制。多租户机制，我们有一些场景的这个客户，他就是需要提供这种多租户的机制，就是它能够实现这种资源的这种灵活的这种组合，包括这种隔离，并且可以混布，就是混布以后还可以实现这种错峰的这种调度，就是白天我可以起一个实时计算集群，那么晚上我可以起一个批处理的集群，是这么一个要求。所以说这样的话会通过这种虚拟化或者云的方式会更灵活，会快速一些，是这意思。对，刚才sorry 啊，那个我们最后那个结果其实有一些没售出来，其实最后接近裸磁盘的性能已经很接近了，这95%以上，其实损失已经非常非常小了。
哎，你好，我问一个问题啊，就是后面有提到的虚拟机高可用这一块，就是说你们扩展到256个节点这一块是用 Peacemaker 本身去做的是吧？
是这样，就这一块呢，工作分几部分哈，就是我们最早那个版本，是用的那个Peacemaker 那个方案，但是 Peacemaker 本身它受限于它这个集群的规模应该是到16，我们刚才那一步说的是这个 Peacemaker Remote， 就是相当于是加它的 Remote 节点，这样可以到256个节点，对。
行，
对。
Any questions?
在最后一页的那个网络的 tuning 那边，你有具体的东西可以分享吗？就是说你有kernel 的 parameters、hypervisor 的 parameters， 就是你有没有一些具体的数据是可以 share 的？
这个哪位？这个您是想了解我们的这个调优的过程是吧？这个是一个就是其实最终的效果就是可以达到丢包率和这个是能满足这种特种行业需求。这个从底上到下我们是有的，比如说我们会做这种 NUMA 的绑定，会做这种多队列的这种绑定，多队列的这种调优，包括这个包括这个就是 CPU 的隔离。以及这个网络站的，就是包括虚拟化层面，我们会用这种 vhost 的模式，这是有一套从上到下。这个图的意思就是从上到下，我们是有一套是会从上到下都会调的，包括 guest 里边的这个 OS 也是会经过这种实时的这种 patch。
是，我是想，比方说 OBS，那具体 OS 里面你们调整哪些东西？这个你们能够
这个你是说要 share 是吧？就通过文档的方式 share 是吧？
对。
您能说您是来自哪？
我是通用电气的。
这个没问题，那我们私下我们下面可以交流，这没问题啊。对，没问题，可以，好。
How to decide how much physical memory and persistent memory for best performance?
So the question is that how do we decide the ratio between memory and persistent memory, which one to give the best?
That's right.
So there are a couple of combination, depends on your workload as well. So generally we recommend 1:8 ratio. If you have 1:8 per DIMM, okay. If you have if you have 1:8 GB of memory, you are related to 1:8 times 8. That's 1.5.
1:8.
Yeah.
One physical memory to 8.
Oh, sorry. If you want 1 per DIMM, that means 16 to 1:8. So if a whole, then if a 12 slot, then 1:8 total 1:8 will be like times 8. So generally 1 slot 16 DRAM, 1:8 persistent memory. 32 DRAM, 256.
Twice is
persistent memory.
Best configuration.
Yeah, so we have a list of combination. If you need that, those are shared under NDA. But if you have customers, then we can share those configuration with you.
So any more questions?
So thank you very much, everyone. We do apologize if you don't have problems understanding English and Chinese here, because we thought the foundation will prepare the interpreter. Thank you.
上云的话，那个内存上的优化有，就是云上去虚拟化很多原因在那个刚才那个六讲的时候有内存的优化，它优化了是上一阶段，它的上一阶段一直就原先是要上，就要写到那个预写到本地盘嘛，字盘上嘛，它就加了一块那个像说的那个它是直接使用的。